Okay folks, welcome to the next lecture, and in this lecture we'll be taking a look at exponential decay. So the general decay function is a base with a negative power. And just some of the general rules: the base can't be equal to 1, it must be greater than 0, and our input is a real number. Again, a fraction, a decimal, a whole number. It can be positive or negative. And a typical graph looks like this. So it's important to be able to recognize these functions when you see them, and also to be able to draw a sketch of the curve if that's required. Again, just wanting to note, with log functions we couldn't go into the negative realm. It's perfectly fine with exponential functions to get, have negative inputs. That's no problem at all. The slope of this curve is always negative, and as x increases, the slope kind of gets less and less negative, but it will never become positive. It's always going to have some degree of downward tilt on it as we move from left to right. But that downward tilt diminishes as our input gets bigger. In general, this is the mathematical kind of general equation of a decay function. Only difference between it and the growth function is the minus on the power. As we saw, this is the typical curve. And just some examples: radioactive decay, the temperature of a cooling liquid, determining the time of death, and drug concentration in blood. These are all some examples of decay functions. There's loads of other ones out there as well. So exponential decay, it's the converse to exponential growth, and this occurs where a quantity decreases by a constant factor over a period of time, and it's got nearly the same function, same formula. The only significant difference, guys, is the minus here. The m and the m0 are purely cosmetic. For growth we used n and n0. For decay we use m and m0, and that's in a kind of general case. This is the general decay function. Really important to realize that these letters change all the time. So depending on whatever system we're examining, these functions, if we were looking at, say, decay and intensity, it'd look like this. The crucial bit is this part here. So that's what tells you you're looking at a decay function. The letters will change all the time to suit the system that's being examined. So as a scientist, when you're looking at this function, that's what you're looking for. What's the sign on the power? Is it positive? That's growth. If it's negative, in this case, then we're looking at a decay system. So this is just saying what I'm saying. The only difference between the two is the minus sign, and the use of the letters is pretty much cosmetic. So just be prepared. What you're looking for is that sign on the power. Is it positive? Is it negative? Typical curve, we've seen a few of them. Generally that same shape, very steep negative slope at the start, and then the slope diminishes as the value of x increases. Remember, x is the power. So now, as we did for growth, we're going to need to be able to isolate k. K still has the same meaning. It's the rate of decay per unit time. Then it's often called the decay rate for that reason. And we need to be able to manipulate it. So again, in any kind of an exam scenario or written exam, you need to be able to perform this manipulation. So this is our initial function. We want to get k on its own. We divide both sides by m0. Next, we want to get rid of the base of e. So we use log we get log to the base e of both sides. which we commonly know as ln. Get the natural log of both sides. Now we want to get k on its own, so we divide both sides by minus t. And this is now the formula we use to determine k. We need the initial conditions, we need the new value, and the time it took for this to happen. In the same way as with growth, we can also manipulate this line here to get t. And same idea in this case, just from this line we divide both sides by minus k. And we'll be using this, we always use this function first to determine k, and then any question that asks how long does it take for something to happen, we use that function there. But again, it's very important to be able to perform that manipulation. Don't just kind of plonk this down at the start of a question in a written exam, because you won't get too many marks for it. You need to show you understand what's going on. So just some examples. Radioactive isotopes, they decay exponentially as time goes on. It's determined by the decay rate. And different isotopes have different decay rates. So decay rate is the measure of percentage of radioactive decay per unit time. And then the half-life is the time taken for half the initial number of isotopes to decay. So this isn't, my little animation isn't working so well. So it's just showing here on the right is it starts. I'll wait till it clocks back to the start again. So it's decaying. So here we have a full amount, and after 4 hours, say, half of them have decayed. Now another 4 hours, half of what was left decays. Another 4 hours, half of what was left decays again. And it continues. So it's actually a little bit like Zeno's paradox. You know, how long does it take for something to decay completely? It can take a very long time. And just the half-life, say, of carbon-14 is 5,730 years. So this is why radioactive material is so hard to store safely, because it has to be stored literally for thousands of years. Here's just another example of the same thing shown on a graph. The half-life of strontium-90, I think it's about 26.7 years or 5 years, something like that. So here, say if we started with 10 grams of strontium-90, after 26.7 years, there'd be only 5 grams left. Now, over the same period of time, again, another 26.7 years, half of that 5 grams would have decayed. We've now got 2.5 grams. Another period of 26.7 years passed. We've now got half of that again, 1.25 grams, etc. The danger is still the same, so it's not like it's losing it. You know, if you go near either of those samples, any of those samples, they're still going to be equally dangerous, because the radioactive material given off, alpha particles, beta particles, can be very dangerous to humans or any biological form. So another example, cooling of a liquid. So if you have say a bath of water at 100 degrees and a cup of tea at 100 degrees, and they're both in the same room, instinctively you know the cup of tea will cool down quicker. And this is all to do with the exponential decay. There's simply a greater quantity of heat in the bath of water than there is in the cup. Their temperatures are the same, but the heat they contain, the heat energy in the water, is much greater than the heat energy in the cup. So cup of tea cooling down of a reactor vessel in a pharmaceutical facility, and in a more morbid sense in a dead body. So when you see CSI and stuff, and the pathologist goes in, kind of touches the body and goes, oh, he died 6 hours ago, that's completely unrealistic. It's actually a much more scientific process than that. And in the last example in this lecture, we'll actually take a look at how that maths is actually done. So this is just given an example of a typical decay curve for a cooling body of liquid. Temperature is in Kelvin this time, so that's why it looks like the numbers look a little bit big. But again, it's got that typical exponential decay shape. And what drives this is K. K is the rate of decay per unit time. Drug concentration in the blood also follows an exponential decay, and very often chemists and pharmacists would talk about the half-life of a drug. And usually once a drug has gone through about 4 or 5 half-lives, it's no longer effective. But if you did a drug test, traces of the drug would still show up. So it's very important from a pharmacist's point of view to try and get the dosing schedule right, that there isn't an accumulation of the drug in the patient system over time. Again, it's a bit beyond my pay grade to kind of discuss it any more than that, but you guys will kind of encounter it as you move further through your careers. So now we're going to take a look at a typical example. Just looking at that previous one, the drug concentration in the bloodstream. So concentration of a drug in the bloodstream follows an exponential decay. So that'll always be part of the question. You'll see the word exponential decay, which tells you must use the exponential decay formula, which we have here. Now, just to go back there before the formula, take a look here. We have milligrams, and then it decays to 520 micrograms. So we've got to kind of normalize our units. My advice would always be bring all units to the lowest kind of unit. So I would bring everything to micro first of all. And I hope you're okay. 125 milligrams per liter into micrograms will give us 1250 micrograms per liter, because there's 1,000 micrograms in a milligram. So that'll be one of our first things you need to be aware of. Watch your units very carefully. Now we have an initial condition, we have a new condition, 520 micrograms, and we have a time period. So we have enough information now to determine the value of K. Once we've determined K to 5 significant figures, we can now answer the following questions. What will be the concentration after 1 day? How long will it take for the concentration of the drug in the blood to decrease to 200 micrograms per liter? So we'll take a look. Now, I'm just going to drop the formula in here. I've already done the maths. I've showed you how to perform this manipulation. Notice how, again, the minus is just floated up to the top, but it's still a negative fraction, so to speak. And we feed in the values from the first line in the question. So the first line in the question always gives you enough information to determine K. Initial value, like I said, 1,250 micrograms per liter. It's essential your units are consistent throughout these problems, otherwise your answer will be meaningless. This decays to 520 micrograms per liter in 4.5 hours. We feed these values into the function, and then we determine K to 5 significant figures. Just what this value means, there's a 19.5% decrease in drug concentration per hour. So it's really important to try and understand what K means, rather than just dumping it in there as a figure. That's what it's telling us. It's the rate of decay per unit time. So now we've got K, we can answer part B and part C. What will be the concentration after 1 day? We just use the formula. Again, the initial value always stays the same. We're going to keep with micrograms. K we've just computed on the previous slide. And what would be the concentration after 1 day? Again, we need to bring everything to consistent units, 24 hours. We feed these values in. Make sure you have your minus in there, otherwise the concentration of the drug in the patient's blood would be increasing. And after 1 day, the concentration of the drug would be 11.6 micrograms per litre. So that's part B. And part C, how long? As soon as you see how long, we need to have manipulated our function for time. I did that back on the previous slide. And again, we feed in the values from the question. M0 is still the initial concentration. Now, the new concentration, this is what we're interested in, the 200 micrograms per litre. How long will it take to decay to this new value, M? And K, again, is the same as what we calculated from part A. Feed these values into our function. And we get our answer then, 9.4 hours. So the one thing, guys, is the process is the same. Even though the scenarios might change all the time, we might be looking at drug concentration, we might be looking at growth situations, decay situations. The process is the same, and once you recognize that process, you'll be able to tackle any problem. So the process involves always find K first, and then there's really only two questions can be asked. What will be the new value after a period of time, or how long will it take for the process to reach a particular value? So if you look back through the examples, you'll see that kind of mechanical process been repeated again and again. Process, so pause the video. Here we have the information you need to calculate K. And then what will be the temperature after 12 minutes, and how long will it take for this body of liquid to cool to 20 degrees Celsius. So it's the exact same process. Another example here, different scenario, but same process. The charge remaining in a capacitor follows an exponential decay. So a capacitor is just simply a part of a circuit. I won't get into it in too much detail, but if we were to build a simple electrical circuit like this, and we had a little light bulb, here's the light bulb. A capacitor simply acts like a little battery. So if we close the switch, the current would travel around, and the first thing it would do, it would fill up the capacitor with charge. And then once this was full, then the light bulb would light up. So what would happen if you were looking at this light bulb? It wouldn't brighten instantaneously. It would brighten slowly over a period of, a short period of time. But what then happens is when we close the switch, the capacitor charges and the bulb lights. Takes a very short period of time for it to reach its full brightness. But if you open the circuit again, then what happens is the capacitor loses its charge. So the bulb wouldn't just switch off when we opened the circuit. The bulb would very slowly dim. Now, you guys wouldn't remember this, but old TVs used to work like this. When you switched off your TV, you'd see these little dots fading slowly into the distance with old cathode ray tubes. Most of you guys wouldn't have seen that unless you were watching your granny's TV. But capacitors are used to protect delicate circuits, so there isn't a surge in power when you switch on or switch off. But essentially, the charge in a capacitor decays exponentially. So, there's lots of different scenarios where exponential decay occurs. So don't be put off by I don't expect you to be familiar with the scenario, but I would expect you to be able to perform the maths. So again, we just calculate K. always the 5 significant figures. And then answer what will be the charge after 1 second, and how long will it take for the charge to decrease to 150 coulombs. And again, coulombs can be measured in millicoulombs, microcoulombs, nanocoulombs. It's just another unit. So even though the scenario would be unfamiliar to you, I'd be surprised if you were kind of familiar with capacitors and their charging properties. But the idea is that the maths is universal. Regardless of what scenario we're looking at, this mathematical process remains the same. So have a go at those questions, and now we're going to take a look at what's called the dead body problem. So there's a lot of information here, and we just have to talk through it. So a body is discovered in a hotel room. At 9:15, the police detective found the body's temperature to be 92 degrees Fahrenheit. An hour, 2.25 hours later, so the body hasn't been moved, a medical examiner records the body's temperature at 86 degrees Fahrenheit. So now we have our initial condition, and we have a new condition, and we have a time period in which this occurs. But there's a little bit more detail we have to consider. Assuming the body's temperature follows an exponential decay, and that the room has a constant ambient temperature of 73 degrees Fahrenheit, determine the time of death of the victim. So this ambient temperature thing is very important, and we'll discuss this in more detail on the next slide. Because really what happens, guys, is even with a cup of tea, if you have a cup of tea and it's at 100 degrees, and you leave it in your bedroom, say, for a day, the tea won't cool down to 0 degrees. It will only cool down to the temperature of the room in which it's in. And that's the ambient temperature. So we actually have to ignore any values below the ambient temperature. They're not what we're interested in. We're interested in the difference between the time of interest and the ambient temperature. So when we're measuring any values, this is what we're looking for. This would be M0 and this is M. So I've done it better on the next slide, so I'll just explain it hopefully a little bit better. So this is our scenario. We're looking at degrees Fahrenheit and our output, time is our input, and this is the ambient temperature. So the body will never cool below that. It wouldn't make any sense. It'd actually be you'd be going against the laws of thermodynamics, which are pretty much the most powerful laws of physics in the universe. The laws of thermodynamics cannot be broken. And this is the kind of pathway of the body's temperature decay. Now at 9:15, the body's temperature is recorded at 92 degrees Fahrenheit. Now, in terms of our problem, guys, this is T0. This is the initial time. The first time a measurement is taken, anytime in an experiment, the first measurement is nearly always called T0, initial conditions, the first measurement you take. So we're not actually interested in 92 degrees Fahrenheit. We're interested in is how hot was the body compared to the room? What was the temperature difference between the body and the ambient temperature? And in this case, it's 19 degrees Fahrenheit. So that's M0. Now, an hour, 2.25 hours later, the medical examiner takes the temperature of the body. And again, that's 86 degrees Fahrenheit, but it's not really the 86 we're interested in. We're interested in the temperature above ambient. That's M. And now we know the time between these two occurrences. So then, once we've worked out K from this information, that's M, I wrote M0. So here we have initial conditions. Here we have the new temperature, and we have the time difference it took for this to occur. Now we can calculate K. Once we've calculated K, guys, what we're actually interested in then is when was the body at normal living temperature, which is 98.6 degrees Fahrenheit. Because most human bodies are generally, that's the temperature of a healthy human. So what we want to do then is work out how long before T0 was it that the body was at this temperature. And again, we're not interested in 98.6. We're interested in the temperature above ambient. So we're asking when was the body at this temperature above ambient. But again, we have to calculate K first. So we'll take a look. Remember our values. There's M0. That's the initial conditions when the police sergeant found the body, the police detective. Here's the medical examiner. That's the new temperature. That's M. So M0, M, and T. We're going to calculate K from that. And then we're going to ask how long was it for the body to reach this temperature. Now, because we're going back in time, our T value is going to be negative. But we just interpretate that T was minus 150 minutes. Well, the person died 150 minutes before the police detective took the first temperature. So again, the maths is the same, but there's just another layer of understanding of dealing with ambient temperatures. So that's what we're looking for here. When was the body at 25.6 degrees Fahrenheit above ambient? That's the real question we want to answer. We need to find K, M0 19, M 13, and this all happened in 135 minutes. 2 hours and 2.25 hours. But bring everything to minutes, guys, for accuracy. Feed these values into our function. And now we've got K. Notice again 5 significant figures. So now we've got K. That's the little engine that drives our problem. We now want to find T. So we use the manipulated version again. Looks very similar to the previous version, but it's now manipulated for T. M0 is 19, and M, the new temperature, is the 25.6 degrees. When was the body at normal temperature, which is 25.6 degrees above ambient? And we've worked out K. Feed these values into our function, and we get minus 106 minutes. So that's 1 hour and 46 minutes before the police detective took the first temperature. So then the person died approximately 1 hour 46 minutes, but they were found. Often this is quite hard. It's quite a kind of a brain exercise to try and figure it out. But when you work it out, it's reckoned that the person died at about 7:30, 7:29 a.m. Obviously, there's always a little bit of leeway, but you could safely say that the person died sometime around 7:30 a.m. And that, guys, is the maths that goes behind forensic science. It's not simply a case of coming in, picking up the person's wrist, looking up into the air for a minute and saying, oh yeah, he died about 7:30. There's a lot more maths to it than that. And the crucial thing all the time is the ambient temperature. That's the crucial driver. And has that ambient temperature changed? Is it a constant ambient temperature? Is it not? If it's not a constant ambient temperature, then the maths gets a lot more difficult. So now, there's just a dead body question for you guys to have a go at. So pause the video. So sorry, that was a little bit quick. So same idea though, calculate K from this. Make sure you subtract the ambient temperature from everything. This one is in Fahrenheit, like the previous example. And then there's another example. And in this one, all the temperatures are in Celsius. So just make sure you take the ambient temperature from all the values. And here we have the normal body temperature in Celsius is 37 degrees. I think it's something like 36.8, but we just rounded up to 37 for ease of calculation. So that, guys, kind of finishes us up. I hope makes sense, and we shall chat to you again for the next one. So thanks for listening. Chat soon.